Hi, everyone. So the office hour this week is moving to? Thursday, same time.
Yeah, go vote.
And it's so that you can all go vote. And so he can go vote. I don't even know exactly for what. I haven't keeping track, but go vote for something good. And what we're going to do today is continue the discussion about lossy compression, which Pulkit started. Oh, yes.
Can we have like bigger font sizes?
Okay. Thanks for the reminder. Constantly remind until we get to the right size. Lossy compression that Pulkit began to expose. We're going to further develop this notion and the setting around lossy compression and get to also the notion of lossy compression and rate distortion theory and the rate distortion function, which is sort of the analog and the extension of the notion of entropy from lossless compression, which kind of emerged as the answer to what is the fundamental limit on lossless compression. We're going to see that the rate distortion function is what emerges in characterizing the fundamental limits on lossy compression. And for that, we're going to start with reminders of some of the most basic quantities that we've already been exposed to extensively in the context of lossless compression. And first and foremost was the notion of entropy, right? So if we had, say, a random variable or random object x, which was discrete, so x is a, let's say, a discrete random variable, okay, random variable or random object that takes values in some discrete, finite, maybe alphabet, then it made sense to talk about its entropy, right? So then we can talk about the entropy of x, right? And that was, so we denoted it by h of x, and that was defined to be, right, the sum over all the possible values small x that this random object can take, the probability that it takes that value times log, by default, base 2, log base 2 of 1 over the probability that it assumes that value summed up over all the values. And we saw how fundamental this quantity is in the context of compression, lossless compression. It answers the question, right, even more specifically, if your data were to come from or be generated by this sort of a source, if it were like a memoryless, right, like if it were IID according to the distribution of this generic x, right, then the best that you can hope to do in compressing data coming from such a source, even if you try to be as as resourceful as you can wish for and work in blocks, large blocks, the best that you can hope to do is, in terms of compression, is these many bits per source symbol, right, per component of your data, which is generated IIDX. And right, and now of course this carries over, kind of trivially almost to, let's say, if you have a pair, right? So now x and y are, a pair of discrete random variables. right? Then we can talk about their joint entropy. So entropy of the pair X, Y. And we denote that by H of this pair, right? The H of X, Y. And that is really nothing new. It's nothing but this entropy, this time associated with what random object? This time the random object is this pair, right? Just like X was a random object and took values in some, space of possible values. Well, now this pair of variables is also jointly a random object, taking values in some alphabet of pairs. And so it's really exactly this thing. It's the entropy associated with the random object, which is the pair xy. So it's going to be the sum over all the values small x, small y, that this pair of random objects can take. The probability that x is equal to small x and that y is equal to small y, log of 1 over this probability. Okay, so obviously, in terms of operational significance, it carries over from the operational significance of this. If your data happens to comprise IID pairs coming from, the distribution of this pair, then the best that you can do for compressing this data is this, in terms of number of bits per pair. A slightly, maybe less trivial extension of the notion of entropy that we've already seen is conditional entropy, right? So let's say the conditional entropy of, let's say of X, of one of these random objects, say X given the other, given Y. Right? So that too we defined and we used, and Shubham used it also in the context of modeling sources that go beyond IID. So there, the conditional entropy of X given Y is, probably the most natural way of presenting it is as a sum over all the possible values that this Y variable can take. So a sum over all the small y's that Y can take. And then we're going to take the probability that this random variable or object assumes the value small y. That's going to be the weight that we assign to the conditional entropy of X given that Y is equal to small y. Okay? And what is this conditional entropy? That X is equal to, of X given that Y is equal to small y? Well, that's really back to this notion of entropy. Okay? This time associated, so, entropy in the end, right, even though we denoted H of a random variable, it's really a function of the distribution of that random variable, right? So here, this entropy is a function, right, of, the probability mass function that describes X, right? Well, here, this creature is exactly this creature, okay? The role of the probability mass function now is played by the conditional probability mass function of X when we know that Y takes on this, particular value, small y. Okay, so this thing is precisely this thing, right? So I'm going to sum up over all the values, small x, that x can take. This time, it's going to be the role of the probability mass function on x will be played by the conditional probability mass function on x, given that y is equal to some value, this particular value we're conditioning on. Okay, so again, I'm assuming this is familiar, and in fact, one thing that you've seen, so this we gave it, right? This has the notation h of x given y, right? H of the random variable x given the random variable y. Again, it's a function really of their joint probability mass function. And here it is explicitly. This, again, in the end, this is a number, right? Again, I know sometimes for some of you the notation, and I feel for you, for some of you, this is sometimes confusing because, wait, h of x, it's a function of x, so it's not a random variable, right? It's a number that depends on the distribution of x. And so here too, right, this thing is a number, as are all of these, right, for any small value y. This, these are different numbers. And and one of the things that you'll recall is that, the property of this conditional entropy is that conditioning reduces entropy. So the conditional entropy of x given y is always no more than the entropy of x, right? So recall, and that's also, pretty kind of intuitive, right? If we think of also of entropy as the notion of uncertainty, then you're on average, your uncertainty on x, given that you know something like y, information can only help to reduce the uncertainty. So you're going to always have this relationship, even though, and this is also something that Shubham pointed out, it's possible that for some specific values of y, this thing is suddenly larger than the entropy of x. Suddenly, maybe there's some value of y which is kind of atypical and throws you off, and suddenly you see, wait, y assumed that value? All of a sudden you're totally clueless about what x might be. So maybe, but on average, when you average these over all of the possible, over all the possible values of y, and you give them the appropriate weight, then you're always going to have, on average, reduction of uncertainty with knowledge of something. In this case, knowledge of y can only help reduce your uncertainty about x. And also operationally, in the context of compression, this was also kind of implicit, at least, if not explicit, in some what Shubham talked about in the context of compression, right? This corresponds to, for example, the fundamental limit on how well you can compress, let's say, data coming. Let's say if your data is coming, let's say you have pairs coming IID from according to this pair, xi, yi's, and then you have the sequence of y's as side information for your compression. So both encoder and decoder know the y sequence. Now we want to understand what's the best we can do for compressing x. And the best that we can do is, in terms of bits per source component, is going to be this conditional entropy. Okay, so obviously, side information can only help you to do better. You can always ignore it. So we're always going to have this relationship. Okay, again, I'm assuming that this is kind of familiar, And, but of course, feel free to stop me at any point. And this is enough to present possibly the most important new quantity in today's lecture, which is the mutual information between x and y. Okay, so maybe it makes sense if I continue here. Can I continue here? Okay, this is going to be right. This is going to be a test to those who are following me, so you know the order. So now we can talk about, in the context of x and y, we can talk about the mutual information. Okay, between x and y. And that we denote, for historical reasons, by I. Well, okay, it doesn't make sense, I information. And we denote it as I, and then we instead of x comma y, for historical reasons that I myself don't fully understand, we're going to write semicolon. So I, x semicolon y is our notation for the mutual information between x and y, which is defined as, or let's say in the context of our current context of discrete random variables, it can be defined as the entropy of one of the variables plus the entropy of the other minus their joint entropy. Okay? So that's what mutual information between x and y is. That's how it's defined. And we can immediately extract or glean some properties of it. So, and in fact, maybe, so let's look at some properties. Now I'm going to totally annoy many of you. Now I'm going to continue here. So I'm going to delete this part. Oh, I could actually continue here. Okay, yeah, this is going to be good. So then it'll be only for...
Only like half of that whiteboard is visible.
Oh, this part?
Yeah, like half of it is visible.
Oh, this part?
Yeah, pretty much.
Okay, well, let's see if I can pull this off, or if I can make use of this real estate. I mean, after all, we're talking about compression. We can't waste space. So let's look at one alternative kind of representation for mutual information. So let me play with this a bit. So I'm looking at the mutual information, and so it's equal to the entropy of one of them plus the entropy of the other, right? Minus the joint entropy. And the joint entropy, as you've seen, right? One of the properties of joint entropy you have seen is that it can be decomposed to the entropy of one of them, right, plus the conditional entropy of the other. Right? So this is one way of decomposing or representing the joint entropy. Everyone okay with this? Great. So now we're getting to, right, so these guys cancel. So I'm getting h of y minus h of y given x. Okay, and similarly, I could have decomposed this as, let's say, h of y plus h of x given y, and then I'd have gotten that this is the h of x minus h of x given y. Okay, so I guess properties. Well, okay, a few things, and this is a bit. Sorry for the mess in the order, but I guess one property which is actually immediate from this presentation is that it's kind of symmetric in x and y. So mutual information between x and y is equal to the mutual information between y and x, right? I guess one way of seeing it is from this presentation, because what are we seeing here? It's the entropy of one guy plus the entropy of the other, right? So that's invariant to the order between them, minus their joint entropy. And it's also pretty, I hope, self-evident that, because entropy really is invariant to, let's say, relabeling or, the order of the elements of the alphabet. So the entropy of x and y is equal to the entropy of y and x. So it's really about, just potentially a different ordering of the values that these pairs could take. Right? So this too is invariant to the order between x and y, and therefore this whole thing is invariant. And then the second thing, which we can easily glean, say, from these representations, taking this into account, that conditioning reduces entropy, is that the mutual information is always non-negative. And a third property, which I'm not going to get into, and maybe it'll be a homework. Otherwise, you're just going to have to wait for next quarter to take 376 and or look at the class notes from 376, is that there's another representation of mutual information, which personally I love most. And that is, so after a few additional steps, you can also get to a representation of mutual information as relative entropy. Remember relative entropy? Everyone remember relative entropy between two probability mass functions? Everyone remember that object? Great. So with a few lines, additional lines of work, you can also show that this is equal to the relative entropy between the, I'll write it like this, the joint the probability mass function that governs the pair xy, and the product probability mass function. So the probability mass function on the pair xy, when they each maintain their marginal distribution, but they're independent. Okay? So that's another alternative representation of mutual information. And some of the reasons I like it is, number one, it gives you another, I think, intuitive sense of what mutual information is. It's a measure of the degree of dependence between the random variables, right? The more dependent they are, the farther away their joint probability mass function is from probability mass function where they're independent. okay? And so the larger the mutual information will be. And the more close they are to independence, in fact, like when they're independent, in fact, only when they're independent, will the mutual information be 0. And this is one of the ways of seeing it, because, only when they're independent will their true joint probability mass function have a relative entropy 0 with respect to the product probability mass function, right? So, and then the other reason why I love most this representation is that it carries over, and on this, again, you're going to have to trust me for now, and maybe even for this whole course, that even though everything we did here was kind of assumed that x and y are discrete, right? So then it made sense to talk about their entropies, their joint entropy, their conditional entropy. But in fact, mutual information carries over and is completely natural. So unlike entropy, which doesn't make sense for continuous random variables, mutual information makes total sense for completely generally distributed random variables. So x, y can take values in wherever you want. They can be discrete, continuous, take values in the real line, take values in abstract functional spaces, the whole sample paths, whatever you want. Mutual information is still well defined through, in fact, a very natural generalization of relative entropy. You can always talk about the relative entropy between two distributions, not necessarily probability mass functions, but two distributions that can govern arbitrarily abstract random objects. And so you can always talk about a relative entropy between their joint distribution and the product of their marginals. And again, those who want the details will be motivated to come back for more in the next quarter, and also maybe to an extent some of this stuff, how, let's say, mutual information extends to some forms of continuous random variables, as the case might be. If and when we will need it, we will, have you guys work a little to understand how things extend. But for today's discussion, it's fine to just, let's say, initially just focus on discrete random variables, and then at some point just have some faith in me that this thing extends to general, also continuous random variables. So, any questions so far? And so now we're going to start. So how does this have anything to do with lossy compression? Right. So far, just like with entropy. Okay. If you didn't take a course on compression, you'd look at this and you say, okay, maybe there's some reason to believe it's a nice, measure of some uncertainty. But then, you realize that, okay, it actually answers a very fundamental question in lossless compression. So mutual information, too, many people, from all sorts of fields, just enjoy this as a nice kind of measure of dependence between random variables. So they use it for all its nice properties, and there are several other nice properties, just as a statistical measure of dependence that we might expose you to in some of the homework. But much more fundamentally, it arises in answering the most basic fundamental question in lossy compression. Okay, so let's remind ourselves the general setting of lossless compression. Okay. Okay, so let's say I have n source symbols that I want to represent. x1, x2, xn. And, right, so I'm going to encode them. So I'm going to design an encoder that represents this n tuple in, hopefully not too many bits. So it's going to output some bit representation of, let's say, m bits. And then the idea will be that a decoder at some point is going to read this succinct representation of m bits, and from that come up with its reconstruction. And when we talked about lossless compression, then here the decoder was required to come up with exactly the original data. So we would here require exactly x1 up to xn. But in the context of lossy compression, we're okay. We might be okay if what the decoder comes up with on the basis of this compressed representation into m bits is something else, hopefully not too far off from this source from the original data. And so we usually also quantify. What does it mean, not too far off? Usually you'll specify to me some distortion criterion. Let's call it D, which for today it's going to be kind of interesting enough to consider, as we often do, kind of so-called component-wise or symbol-by-symbol distortion criteria. So usually you'll specify to me a distortion between pairs, a distortion that looks at the distortion between, the ith component here and the ith component here in the reconstruction. And then I'm going to judge the overall goodness of this reconstruction according to, let's say, the average, right? The average, or if you will, the per symbol distortion. And of course, this is, as in the lossless case, we're going to be modeling things probabilistically, right? This is going to come from some probabilistic source. So this is a random variable. We're going to look at its expectation. Okay, so this is what we're going to colloquially refer to as the distortion. Right? So this is the distortion that your scheme achieves. If you want to be totally elaborate and explicit, you're going to say, I guess the per symbol, right? Because it's normal, per symbol, because we look at the sum of all these individual distortions and normalize, and then we take expectation. So per symbol, expected distortion, but usually, we just talk about the distortion achieved, and we mean this. And then, of course, the question is, okay, obviously you want the distortion to be as small as possible. And of course, so distortion criteria that you guys may, or some of you are familiar with is, for example, Hamming. So let's say Hamming is a distortion criterion that makes a lot of sense in the context of discrete data. And then we just look at whether or not the reconstructed symbol is equal to the original symbol. So it's an indicator for whether the reconstruction symbol is I mean, if the reconstruction symbol is equal to the original symbol, then there's zero loss. And otherwise we count it as a loss. Right? So that's called, so examples of distortion criteria. Right? So this, so maybe this is one, and this is called Hamming distortion. And then, as we said, like lossy compression is also, and in fact, in some ways, even much more interesting in the context of continuous data, where you have no choice but to do lossy compression. And then, of course, let's say if these are real valued, right? These are, I don't know, sensor measurements. These are real valued. Then it makes a lot of sense to look at something like squared error distortion. Okay, so, usually in an application, you'll tell me what is the right, what's the most kind of relevant distortion criterion. Let's say if this is let's say genomic data. These are nucleotides taking values in a space of size 4, and then it might make a lot of sense to talk about Hamming and to tell me, yeah, I'm willing to suffer a bit of Hamming distortion, positive Hamming distortion, meaning in the reconstruction, every once in a while, you're going to get a base pair incorrect if it means that we're going to need way less bits here in the representation than we would if I required totally lossless compression, right? In which case we would need the entropy. So maybe now, if I'm willing to suffer some positive Hamming distortion, maybe we can get away with less bits. And so, okay, so there's a distortion, and then the question of, okay, what does it mean, getting away with less bits, right? So concretely, we talk about the rate, just as we did in lossless compression. We had the compression rate, which was the ratio between the number of bits in the compressor representation and the overall length of the sequence. Right, so it was like, how many bits do I need per sequence component? So that was the rate, and so here too, that's the rate. It's going to be the ratio between the number of bits, m, that my compressor presentation is requiring, and in how many overall source components did I manage to represent with these m bits. So here it's like n source components. Okay, so that's the rate in bits per, usually you're right, bits per source symbol. Or we just say, bits per symbol. Okay, and we know, again, lossless compression, we know that the best that you can do is, in terms of rate, if you want this to actually equal this, or in terms of distortion, if you want, let's say, the Hamming distortion to be 0, if you want this thing to be 0, then we know what is the minimum rate I'm going to need. That's the entropy. Let's say if these are IID according to some distribution x, it's going to be the entropy of x. But the question is now, if I allow some distortion. Okay, so maybe we can talk. So here's my question, and I'm not going to be maximally sort of formal about it. And I'm just going to write it in words. So the question is, what is the minimum rate needed, okay, for getting distortion no more than some specified distortion level that you're willing to tolerate. Okay, so again, lossless compression, we've answered this. If this D is 0, what's the min rate that we need for distortion 0? And the chorus sings entropy. Exactly. But what is the minimum rate needed if I'm willing to suffer, let's say we're doing Hamming loss, and this D is, let's say 0.1, right? Meaning Hamming loss, D 0.1, meaning I'm okay with this reconstruction getting only 90% of the symbols correctly. Then we should expect to be able to represent the data with less bits to, have a compression rate smaller than the entropy. And this question was answered beautifully, crisply, and quantitatively by Shannon, of course. So Shannon's theorem in this context, or one of Shannon's theorems, so in this context of lossy compression, is that let me also denote. So let's denote the answer by R of D. Okay? So what is the minimum rate needed for achieving distortion no more than D? Okay? When I allow you to optimize over all schemes in the world, arbitrarily complex, sophisticated, using arbitrarily large blocks of data simultaneously, what is the minimum, the best that you can do, optimizing over all of these? Okay, so there's some answer, there's some minimum rate that we're going to need, denoted by this R of D. And Shannon's theorem is that R of D, the minimum rate that you need to achieve distortion no more than D, is given by the minimum mutual information between X and Y. Oh, okay, I should say, so this was very general. I didn't talk about what the distribution of the data might be. So here, again, to be concrete, just like in the context of lossless compression, we talked initially about IID sources of information, so here too. So Shannon's theorem for IID source, so for if the xi's are IID according to some generic x, right? Just like in lossless compression, we know if the xi's are IID according to some generic x, then the minimum rate that you need for lossless compression is the entropy of x. So here, let's again assume the xi's are IID according to x. Then, what's the minimum rate that you need if you're allowing distortion up to D? It's the minimum mutual information between this generic x that represents the distribution of your source components and a generic reconstruction variable y minimized over all joint distributions on xy such that the expected distortion between xy is no more than D.